I hope you've been following the 1 billion row challenge videos with Casey and Marco, who created this awesome series of videos discussing performance, what to expect from hardware, from software, etc. Unfortunately, that series ended because Marco got promoted, which is a shame. But I figured they don't have the monopoly. Why not create the spin-off and continue where they left off? Now, where they ended was they have a Java loop, which is a simple loop that has a byte array and a limit. So they go from 0 to limit and they count the number of new lines that they see. The loop performed not as fast as they expected, and it wasn't clear whether it was Java or it's the hardware. So they generated the assembly code, but it was quite long, so they didn't go into it. So you see here, they look at the JIT watch application. So what I want to do is go through that assembly and explain everything that happens there. Well, almost everything. However, we cannot do this in a single video because it would be overwhelming. And I think that not many Java developers know assembly, so I want to walk you through the assembly. I want to walk you through how to write loops and how to create functions in assembly. Then the code there is actually optimized by JIT compiler. It's not just a regular loop, it's an unrolled loop, so we'll look at that optimization as well. And also there are some JVM specifics, internals like save points, implicit null checks, so we'll walk through that too. And I think it makes sense to show how you can build your own JDK from the source code in order to debug it and in order to debug the assembly code that was generated by JIT. So you can actually go assembly instruction by instruction and see how your code changes the memory and the CPU state, etc. I think we can start. So this is our loop, and we want to write something similar in assembly. First of all, the first complication is there are multiple architectures of the CPU, right? So we have ARM assembly and ARM architecture. This is my CPU, my M2 Apple Silicon. And there are x86 CPUs used by Intel and AMD. Those will have different set of instructions, and they also have a different syntax. I'm using the ARM v8. First of all, this is an architecture as well. ARM v7 is 32-bit architecture. This one is 64, but it's not just the number of bits. It's also the instructions changed. And also there is a variation within syntaxes. Some people put hash before the constants because older syntax required that. The new syntax, the unified syntax, doesn't require that. So a lot of variation, but the structure is the same, more or less. Another difference between ARM and the other one is the number of instructions. ARM represents the RISC architecture, reduced instruction set computer, meaning the number of instructions that it has is smaller. And also, every instruction is a 4-byte word. While in x86, they have variable length instructions, which complicates things for them. But also, in many cases, they have just one instruction, while we would have to write multiple instructions in ARMs. So yeah, they have more instructions and they're variable length. So here's the assembly that I wrote with the loop. Let's look at the main sections. First of all, we have text section. This is our actual instructions. There is data section where we keep variables and constants. And there's a global section where we define the public API, basically. Some other file, assembly, or C will be able to invoke functions if they're declared in .global. Additional variation. At macOS, you have to put the underscore before the public functions. On Linux, you wouldn't need to do that. But it has to be main if you want to run this from the command line. If you want to just invoke that code from C, then it's fine. Whatever function name you want, you can call it that. Okay, so we have text section. Now let's go through the actual code. First of all, these are labels. we can jump to labels. And sometimes we want to jump to labels because we just structured the code this way. Other times a label is basically a function. Main is a special label because when the program is compiled into an executable, during the compilation, this code is actually combined with some scaffolding, and that scaffolding is what calls our code. Okay, so let's take a look at this instruction. This loads a variable. So this is our variable. It's defined here. It has a type. It's a string, null terminated string. In C and assembly, when you define a string, it's not like in Java where you have a class with actual bytes as well as the length, which is stored as a field within the class. And same for arrays. In Java, we have a length within the array. But in C and assembly, if you create a string, it's basically a pointer to the first character. And then ideally, the string is terminated with this symbol, basically a 0 byte. And this way we know where the string ends if we don't want to keep the length of the string as a variable. But if we declare it as this type of variable, then it adds a null termination at the end automatically. We don't have to do this manually. So this is our variable name, type, and value. Now we want to load it. In order to load it, well, it's kept in some section of memory, and it's not necessarily close to our code. So these procedures are used to reference that piece of memory. And the compiler will find this label and will put the actual address relative to this instruction to reference this piece of memory. And this is where we see the difference between ARM and Intel x86 architecture. In Intel, this would be a single instruction, load a variable, but in ARM, we cannot afford doing this. The reason is, as I mentioned, instructions are 4 bytes. So we have some bytes that are actual instruction, then we need to reference some register, basically a variable, and we also need to reference the actual address. So how do we fit it into 4-byte instructions? We can't. This is the reason there are 2 instructions to do that. So this address pointer loads first bits of the address into the variable x2, and then it adds the other 12 bits of the address to the same variable. So it's split into 2 instructions. Very weird, but you'll get used to it. Now this is a register, which is basically a variable, but unlike our Java variables or C variables, we cannot just name them whatever we want. It has to be one of the possible registers that this CPU supports. And some registers are general purpose, meaning you can put any integer, any address there. Others are specific to floating points, and you can run operations like add floating point numbers only against those registers, and etc. There are more special registers. So this one, if it starts with X, most X registers are general purpose, so we can use them for our own needs. So we loaded the reference to this variable to this register. We didn't load the actual values yet. We just loaded the address. Okay, next instruction is move. So move is basically assigning. So in this case, we assign 0 to variable, well, to register W0. Now, W0 and X0 is actually the same thing. The difference is if we were to put X0, it means that we overwrite all 64 bits of that register. If we put W, it means we assign the value to the last 32 bits, and the first 32 bits, because every register is 64-bit, every general purpose register is. So the first 32 bits are going to be zeroed out. So we put the value of 0 into register W0 or X0. Now we put the same value into x15, what will be these variables? And this is the most complicated part, well, at least for me in assembly, is these values. Like, I don't know what that variable means. Is it I? Is it new lines? And it gets worse because there are only so many variables that you can use, so many registers. So you will have to reuse the register for different purposes. So in one piece of code, it's going to mean one thing, but later it's going to be used for a completely different thing. Okay, so in this case, my convention is this variable is always named x15 or w15. And I use 0 register in this case to store the new lines. You will see it oftentimes, because this is the convention, the return value of the function is expected to be in the register x0 or w0. And so I put the new lines into w0 right away, because then I will just return it and that's it eventually. Okay, so we defined 2 variables. We put 2 values into 2 registers. Now the loop starts. We defined a loop label because we want to return back to it. We want to jump or go to this label if we don't want to go out of the loop yet. So this is a CMP compare instruction, and we compare the value within I, this, compared to 13. Why 13? Because I hard-coded the value hello world, which is 13 characters long. Okay, so this is our compare statement, which is basically an if. But this if is actually 2 instructions. So we first define what value we compare to what value, and then we define, are we looking for less than or greater than or equals? So in this case, we're looking for greater than. So when x15 is greater than 13, we want to do something. What do we want to do? We want to branch, which basically means a jump to a label. So when the value reaches 13 and goes beyond that, we jump to this label, which is defined here, which is near exit. So this is our condition in this for loop, but it's reversed, right? Because in this case, we want to stay within the loop while I is less than limit, but this condition means we want to jump out of the loop if the I reached the limit. Okay, so this is our condition to go out of the loop. Now we see this weird instruction, which is basically a load register byte. We can load 4 bytes at a time or 8 bytes at a time with these instructions. But when we go through the byte array, we actually want only 1 byte at a time. So here's how it looks. We want to place it into W3. And we have this variable, we have the pointer to the start of this variable. So we know the address of H. And it's stored, as you may remember, in X2 register. So we'll look at X2 memory address plus whatever is stored in X15. And right now it's 0. So basically, we are referencing this H. So these brackets, they basically mean go and fetch the value by this address. So we fetch H and we put it into a W3. Now we want to compare that W3 or X3, doesn't matter in this case because it's only 1 byte that is filled. We want to compare it with new line. While you can put an actual character right here in the assembly, in reality you will usually see numbers instead of that. So new line is 10. So we could have written this way. Or, which is also common, is to look at the hex. So we can choose whether decimal or hex is more appropriate. And you should get used to hex because we will see more of hex than decimals in the assembly. So we compare whether the value that we loaded, right now it's h, is equal, well, we don't even say here yet whether it's equal or greater than, but the next one says we want to jump to this label if it's not equal. So if it's not equal, we skip this increment because this is x0, this is our new lines variable. We skip this plus plus and we don't do the increment and we go and increment I instead. So it's this I. After we incremented I, we jump back to the start of the loop. So this is actually represented by the following code. We have byte array, we have int limit, we define new lines, 0, we go into while, into the loop, and we say if array I, oh, we didn't define I, of course, int I is 0. So I'm trying to repeat the assembly code that we just wrote. So if, first of all, if I is greater or equals than the limit is greater than limit, we break. So in this case, it should be greater than or equals. If we break out of the loop, if array, okay, we put a value of byte into some variable, b equals next variable. If byte equals, I guess we cannot do it otherwise here. If it's equals, we say new lines plus plus, which is reversed in our assembly code. We say if it's not equals, then don't do this. And we increment I plus plus and we return back. And eventually we'll return new lines. Can we write not equals and skip somehow? We can do it this way, I guess. If it's not equals, we increment. Okay, we can do it this way. We can increment it. If it's not equals, we continue. Not exactly the assembly code that we wrote, because I++ is now here, it's not here. But anyway, in assembly, of course, you can do more than in high-level languages. So let's continue. We incremented our I, and now we want to look at the E, right? So we'll check whether our I is greater than 13. It's not, so we're not jumping here. We'll load the next value. How do we do this? We still have the base address. The base address is the address of the first symbol, but plus I, so I is currently 1, so we have x2, whatever the address is, plus 1, which references this one. We'll look at that address and we'll load the value that this address points to into variable w3, and we compare this register with new line again, and again we skip the increment because e is not equals to /n. If it is equals, then we don't jump, we do this, and then the next line that we continue is this, then this, and we jump back. So eventually, at some point, I is incremented more and more until it reaches 13 or 14, and then we jump out of the loop. And this is basically an exit. This is a system call for exit. 1. This is my particular architecture. On my particular Mac OS, the system call for exit is 1. And then we say, do the system call. This variable, this value doesn't matter. We can put anything here. So we say which system call to call and then actually call it. So in this case, because I was counting new lines into variable w0, that is the variable that decides which exit code to return. So now let's check the working of the program. Ooh, next complication. There are multiple compilers. I'm using Clang, which is commonly abbreviated as CC, but there's also GCC, and on Windows you have whatever compilers on Windows. But in many cases you can either use GCC or CC. So this command takes this assembly file and it generates the executable. Usually there is an extra step between these. We generate an object file because we may have multiple assembly or C or whatever files. We generate an object file for each of them, and then we'll link it all together into an executable. But in this case, because we have just one file, we generate the executable right away. So we compiled. Now I can run this. It doesn't print anything because we didn't call any functions to print anything, but it did return a value from as an exit code from the whole application. And that is stored in a variable, this one, right? If you use Linux or BSD or Mac, this is the way you read the return code from your program. And as you can see, it's 2. Why is 2? Well, it's because there are 2 new lines here. So everything worked, which is great. And I also want to show how to debug this. Yet another complication. There are multiple debuggers. Clang comes with LLDB. GCC comes with what is called GDB. So the way you do this, it's similar in both. LLDB, you say which program you want to debug it. So this LLDB eventually is going to run this program. We say it's loop. I installed some libraries, whatever, some symbols, so it's gonna load them. Now we're in the debugger, but we didn't start the actual program yet. Now we can put a breakpoint, and you either put a breakpoint to some location in memory where the instruction is, or you can put it onto some label. So I want to put a breakpoint. I think this is the syntax: breakpoint minus n name, and in this case, if I remember correctly, no underscore. Okay, so we put the breakpoint, and now we want to run it. So we say R for run. This is our first instruction, as you can see, loading the address, and this is the page number, and this is the location within that page. We're currently on the page this plus zeros here, so this is the page number, and this is how far from that page, so +1, and this is the instruction on that page. So we can press N to continue to the next line, and this is one of the ways we can debug things. I forget how you can watch the registers. Reg read -f D, meaning show us the values of the registers in decimal. So register read. And this way we see all the registers, actually not all of them. We see general purpose X registers, and these we will talk next time what these mean. So right now right now we are on this line. We haven't executed it yet. So we only put the page number into X2, so it has some value. Other registers also have values which are rubbish for now. So next step, we are setting 0 register to 0. Right now the value stored there is 1. Next. Read the register states, and we see it's 0. It's possible to debug things right in JetBrains products in CLion. I'll show you that at some point, but I think it makes sense to learn these LLDBs as well. I'm not a very big expert here. So now we're finally comparing our I to value 13. 13 in hex is D. It's not yet greater than 13, so we're not going to jump. So we will go to this instruction, load register byte. And now we're going to fill the W3 value with whatever is located at that address. Right now, it's rubbish here, so we will go next step. And now when we read the values here, here's the 72. Why 72? Because this is the ASCII code for H. And so on and so on. You can put more breakpoints to other labels, but well, I guess we've seen everything that we wanted. Okay, I think that is it for one episode. That is enough. Probably the next one we will discuss how to call functions in assembly and what functions even means in assembly. See you next time.